So the hope is to go through some of the basics and some of the application of the machine learning in material science. So just as an introduction, I just want to point out that in our everyday life, we are right now dealing with a lot of machine learning algorithms. For example, of course, at the frontier of the technology, Google using it for a lot of its feature, including but not limited to spam detection, smart translation, and of course, personalized search. Alternatively, Facebook uses machine learning for face recognition. Amazon, Netflix, or Spotify all use machine learning to recommend items, movies, and music. And more recently, Tesla has developed AI chips for its self-driving cars. But as a matter of material science, all of these social networks and also social sciences, they have plenty of data that have been enabled them to make sophisticated machine learning for quite a while. But we don't have that privilege in material science yet, but it's suggested that the next paradigm change in material science could be data-driven sciences such as machine learning, and partly this have become available due to the advancement of computational methods, which have generated enough data for us that we can use machine learning models now. Nonetheless, still this data in material science is sparse. So to just simply walk you through the overview of a machine learning algorithm, we always start with a database to use in our training data, which we could later basically train our model based on. So that's one of the most important part. And of course, there are always some data sanitizing within any databases. Once we have our data, the next step is to construct a set of variables in which are able to represent our data and basically be able to make prediction later on. And of course, there are some feature selection methods. Once we have our training data and our variable set, we could go ahead and build the machine learning model. And very important part of a machine learning flow is validating the actual performance of a machine learning model. And of course, the ultimate goal of any machine learning is to be able to predict the properties of unseen examples. I mentioned that the data is the first building block of a machine learning model. So here I want to introduce some of the databases that you could use and people are actually using in material science to construct the models. One of the very nice programs are AFlow and the Materials project, which both of them do high throughput density functional theory calculations, and they have calculated properties of thousands of inorganic materials and have put it online and free to use for everyone. And people are actually using these extensively to do machine learning. Also in material science and chemistry, we have a very nice databases of crystallographic information such as ICSC or PCD. And of course, there is the database of, for example, phase diagram. Another platform that I want to introduce is Citrine. Not only Citrine has accumulated a very useful set of databases, but also it allows simple and intuitive platform to actually do machine learning. And I'm sure Bryce will be able to give you a much better introduction to Citrine. So we have all these databases that we could use for our modeling, but what are the other sources that we could potentially use? Whenever we want to do research, the first thing that we refer to is going back to literature. So literature is a very dense set of data that we have. However, the problem with literature is that it's not written in an organized way. Journal from journal, it's different, and it's very difficult to extract. However, recently research has shown that it's possible to use automatic text extraction, and they've actually extracted data from literature and made model and later designed synthesis recipes, which work pretty well. And this is very exciting. Another source of data, literature is great, but another source of data is lab notebooks. We have literature, but literature is only the report of our success. We only report the successful reactions. But in fact, any successful reaction is usually backed up by tens or maybe hundreds of failed reactions, which could potentially provide essential information for us. And even we learn a lot from failed reaction. It's those failed reactions that step by step led us to the successful reaction. So, and if extracting data from literature is difficult, it's much more difficult from lab notebooks, because every person has a different writing style. Research group from research group is different, and not necessarily all the research groups are even willing to share their lab notebooks or their data. And especially in its old-fashioned format, like it's just very inefficient to use and extract. However, researcher has shown that if one could extract this data and then they have used this data of their group to predict hydrothermal synthesis conditions with a success rate of 89%, which outperforms human strategies. So right now, Citrine and other platforms have started to organize some online lab notebook in an organized way so that the data could be useful in future for everyone to use potentially. So I emphasize on the importance of the data and where we could potentially get our data. But let's move on to machine learning algorithm. So in general, machine learning algorithms are categorized into unsupervised learning and supervised learning. Unsupervised learning is the case that we have data, but we don't have their corresponding labels, meaning that we don't have their target. And some of the examples of unsupervised learning are clustering, which in clustering, the algorithm looks at the similarities in the data to potentially be able to classify them. We have dimensionality reduction, which is very important. One example is the principal component analysis. The way that principal component analysis works is that it takes, because in machine learning we are usually dealing with very high dimensional data. And using principal component analysis, one could reduce this dimensionality while containing most of the variance. And this is very useful, for example, for even visualization of the data, which is not possible beforehand. Another very interesting set of learning is anomaly detection. And in contrast to unsupervised learning, supervised learning is where we also have the labels of our data, and we can directly train the model based on training data and their corresponding output value. Of course, when possible, we prefer to do supervised learning because it's just easier. It's easier and it could be more efficient, but we don't always have this privilege. So unsupervised learning is extremely important and could also be used in conjunction with supervised learning. A lot of the time, at first we, for example, use some dimensionality reduction method and then carry out the supervised learning. Maybe the most common subcategories of supervised learning are regression and classification, which I'm going to focus most of the presentation here on this supervised learning. So for supervised learning, let's assume that X is the set of our feature or variables and Y is the corresponding label. The goal of any supervised learning is to identify a function using X and Y in the training set that is later able to accurately predict the Y values of the unseen examples. Here, for example, in this figure, you see that we have a set of data with X and Y. So this is basically our training set. So we can potentially, as you can see here, we can fit different function F's that perfectly fits our training data. And so therefore, the function that is returned is not necessarily unique. We call the space at which contains all of this function as hypothesis space. But in machine learning, what we care about is the predictive power of the machine. How well it performs for unseen example. Do all of these functions, even though they fit the training data perfectly, are they going to be able to also predict unseen example? And that's what's really mattering in machine learning. We could also apply some constraint, and people, that's what usually apply some constraint on the hypothesis space. For example, in this example, the constraint is that the function could be returned as in a linear form. So I usually find it quite useful to construct a learning framework based on statistical base rules. In very, very simple rule, base rules says that the probability of finding function f after observation of training data x is simply equivalent to evaluating the probability of obtaining data point x using function f and its corresponding probability distribution times the probability of function f before observing any training data. And the advantage of this the base framework is that it has a stepwise learning, meaning that if we have a new data point x2, we can update the probabilities. As you can see here, for example, if we have like the first training data, and then by adding and their corresponding probability distributions, we can add the second, third, and fourth, and fifth training data, and the probability evaluation evolves. But dealing with all of this probability distribution is not straightforward at all. So one could alternatively just simply maximize the posterior probability distribution shown here. Applying the base rule as I showed in the previous slide and doing some transformation, we see to this objective function. And the goal of the machine learning here is to just minimize this objective function. This is at the heart of a lot of algorithms in machine learning. And it contains two terms that needs to be optimized. The first term is called empirical risk. And it's in simple word, how well function f reproduces the training data. And the second term is a regularization term, which is simply the prior constraint and based on the hypothesis space before any training. So now that we have this platform, maybe one of the easiest and most straightforward machine learning regression loss function is least square model. So let's see if we can drive the least square model. So again, let's assume that we don't want to put any constraint on the model. So we only have the empirical risk, which was how well function f could reproduce training data x. So in another word, one could say that if the prediction of function x is too different from the actual label that we have, then our model should be penalized like this. This is also referred to as loss function. For example, if we assume that we have a Gaussian distribution, then the loss function of least square model is just simply minimizing this argument here. So before delving too much into the math, I've created two case studies here for you to walk you through the steps of machine learning. The first case study that I created is creating a machine learning model for prediction of formation energies of the materials, and the second case study is using a classifier to be able to distinguish between cubic and hexagonal crystal structures using machine learning. For creating this code, I use Python within the environment of the Jupyter Notebook and using scikit-learn machine learning libraries. And of course, all of this data will be available for you, so you could also play around with the parameters and use parts of it for your own projects. So let me walk you through the complete steps that one would need to do for machine learning and material science. So of course, the first step to gather a training data. And here, I use materials project data and extract all of my data from here. I only limited my extraction to one-to-one ratio, stoichiometric ratios of binaries, A-B compounds. And for the first case study, which is the prediction of the formation energies, I extracted data from DFT calculations of materials project. And for the second one, I've only limited the compounds to either cubic or hexagonal crystal structures. And of course, I did some data sanitizing. For example, I removed all the compounds that contain element with Z of greater than 83. At the end, my training set includes 694 binaries, which include 521 cubic structures and 173 hexagonal structures. So the next step after building the training data is to construct a set of variables. For this case, I simply used some compositional variables. Here I picked 20 compositional variables. For example, group number, ionic radius, or number of valence electron. And these variables should be able to represent our compound in a unique way. And later, if we want to predict something, we need to also create a similar set of variables, and then the machine will be able to predict the properties accordingly. So also I added 4 mathematical expressions. For example, for the case of the atomic number variable for boron nitride, I added like 5 as atomic number of boron, atomic number of nitrogen, their difference, and their average. So at the end, we have a variable set of 80 dimensions stored in a form of an array. So that means that I have 694 compounds in a dimension of 80. So we are dealing with this kind of matrices. And this will be used as our feature set. But before going to any modeling, the next thing that I do is to split the training data into the data set into training and test set. And the reason to do that is that, as I mentioned earlier, what we are looking for in machine learning is the predictive power. So if I just simply train my model on the training set, then I could easily just overfit, and I can't evaluate the function fairly later on. So I just take, for example, 20% of the data aside as test set, so that it's not contaminated with anything in the model. And further, I've also done some normalization of the data. So we already developed least square treatment simple regression model. So let's use that model to see if that model is capable of predicting the formation energies of inorganic materials. So here, as you remember, I just need to minimize this function. So I write function f as a linear expansion of the coefficients. My coefficients is w1 all the way to w80, and the idea here is to simply minimize the differences of the labels minus the coefficient times training data. And here we are optimizing for the coefficients. So after creating this model, I went ahead to use this model to predict and model my formation energies and predict the test set later on. Here on the left, you see on the y-axis we have the predicted values from machine learning, and on the x-axis we have the actual formation energies. So here, what I wanted to show you is that as I was playing with the splitting of the training and test set, I was getting very unstable results. Sometimes I would get such a regression curve, sometimes a very nice regression curve. And I also looked at something that you see on the right, which is called learning curve of formation energies. And this is, I'm using here R squared, which is coefficient of determinant, which is one of the metrics that we use for the evaluation of a regression, and looked at this metric as the training set size changing. And as you can see, again, with the different splitting of training and test set, I was getting very different and weird outcome. And this is on the training set, the score of R2, and this is on the test set. Nonetheless, these results showed me that the linear regression is not stable here, and basically this problem is ill-imposed for these descriptor sets. So if you remember, I was talking, this framework also contained another term, which is a regularization term. So let's add a regularization term and see to the simple least square model and see if it helps at all. So here I'm adding my constraint here by just adding a coefficient alpha times the square root of the coefficient. And now I have to optimize for the optimum value of alpha. So here I'm ranging alpha from 100 to 0.01. And the training set, the R squared of the training set is shown here with the blue regression curve. As you can see here, as I'm decreasing the alpha, the training data performance increases and increases. But if you look at the orange curve, which is score on the test set, you see that there is an optimum value, and after that the performance decline. That means that for the values smaller than alpha 1, the model is just simply getting too complex in the training data and simply overfits. So that's one of the the importance of evaluating the metrics on test set instead of training set. So using alpha equals to 1, I was able to get a regression model here. Here the dashed line, the diagonal dashed line, is our ideal line. So ideally we want all the data point to be on this line. But you see that we have some scattered. So here the R squared is 0.75. Another matrix that we use is root mean square error. The smaller root mean square error is, the better the performance of the model, and in this case the value is 0.38. So it looks like we are able to at least get a reasonable model using this model adding with the addition of the regularization term. This is also called and referred to as ridge regression. So, but let's move on to some more sophisticated method. For example, the case of support vector regression method. The idea behind support regression method is also very similar. We also have a linear function f in a linear format, and we simply want to minimize the coefficient subject to some constraint. And basically, the goal of a support vector regression is to find a function f that has at most epsilon deviation from the target, but it's not always while being as flat as possible. The reason that we are looking for flat function f is because as function f gets more and more complex, it's less likely to be able to generalize. So, but the problem is that usually the optimization methods are not that easy. The optimization problems are not that easy. So it's not possible to contain all the training data within the bounds of epsilon. So for that purpose, we add a regularization term to allow for some slack in the training data, so that to make our optimization problem feasible. And the amount that we allow this slack is controlled and determined by coefficient C called cost function. So basically, the cost function determines the trade-off between the flatness of function f and the amount which deviations larger than epsilon are tolerated. So using that, we are able to most of the time carry out the optimization. But even then, with this construction, the optimization problems could be much more complex. So that's where the power of SVM comes from. And SVM could use a kernel function to map the data into high-dimensional feature space where the optimization actually is feasible. Unfortunately, converting the data and mapping the data into higher dimension decreases the power of interpreting the data significantly. So, as I mentioned, we have a parameter called C here that we need to optimize for support vector regression. We also have another parameter called gamma in the kernel function that needs to be optimized. To optimizing these two parameters, I'm going to use a 5-fold cross-validation. The idea of cross-validation is that if we have our data, 5-fold cross-validation is going to partition the whole data set into 5 partitions, with one being considered as a test set and the rest of them considered as a training set. And this is repeated 5 times, so that all the training data are once in training set and also in the test set. So doing cross-validation has some advantages. For example, it helps saving data for training. And this is sometimes important when getting data is extremely difficult and expensive, and our data set is very sparse. So this another advantage that cross-validation has is helps avoiding overfitting. Also, it helps tuning the regularization parameters, which I'm going to do with C and gamma here for support vector regression. And at last, it also allows fair evaluation of the performance. But for best practice, it's best to set aside the test set beforehand, before even performing cross-validation, and later also do a cross-validation method. So here, I use the cross-validation method alongside the support vector regression to optimize for cost and gamma value. And here, the color bar is an indication of the validation accuracy. So it turns out that the best value for C is 10, and the best value for gamma is 1. So using this parameter, I went ahead and used support vector regression. On the y-axis, you see the predicted formation energies, and on one y-axis, you see the actual formation energies. Here, the root mean square error is 0.32 electron volts, and R squared is 0.87. And comparing this with the previous ridge regression method, we see a significant improvement. So the last thing that I want to emphasize here for the formation energies is comparing the learning curve, comparison of the learning curve for ridge regression and support vector regression. As you can see here, support vector regression for both test score and training score outperforms ridge regression. But what I also want to, as the size of, and this is as the size of training set data changes. But what I also want to emphasize is that if you look at the test score of support vector regression, you see that as the training data increases, it has a slope. It has a positive slope, which means that if we add more training data, it could potentially improve its performance. Another point that I want to emphasize is that if you look at the green curve here, you see that the support vector regression on training data is almost perfect. And that's another indication that you should just evaluate, you should really care about evaluating the data on the test set, because training set here is just simply overfitting. And if you report such a statistic and later use some prediction like a test set here, you see that the performance is not as good. So so for this case study, I want to emphasize that we were able to get reasonable models using very modest number of training data and simple regression practices. So let's go to the second case study, which is a classification of crystal structure. Just as a reminder, I only extracted one-to-one ratios of AB binaries, and we have only limited them to 521 cubic structures and 173 hexagonal structures. So the question here in the classification is that, are we able to simply use compositional descriptor and be able to distinguish between different crystal structures? So for doing that, I'm using support vector classification method. The math and idea behind support vector classification is very similar to support vector regression, with the difference that our labels are discrete in this case instead of being continuous. And the goal of the classifier here is to define a hyperplane that best classifies the training data. But as you can see here, there are different hyperplanes that we can choose that all perfectly classifies the orange circles from gray circles here in this case. But the question is, which one's the best? And which one at the end have the best predictive power? Because that's what we care about. And the idea is that the ideal hyperplane is the one that maximizes the margin between two classes. And of course, if the data is a little bit more complex, we could also, like regression method, introduce some slack parameters to account for that. But again, in real life, never the data is so easily separable. So, and this is again the power of SVM, which is able to project the data from input space to multi-dimensional feature space, where two classes are actually separable using a hyperplane. And to doing that, we use a kernel function. So again, like regression, I use cross-validation to optimize values of cost and gamma, and C equals to 10 and gamma equals to 1 work the best here. And the classification accuracy turned out to be 0.87, which is pretty reasonable, evaluated on the test set. So another very important characteristic and the evaluation metric in support vector classification is a curve known as receiver operating characteristic known as ROC curve. So in the ROC curve is plotting true positive rate versus false positive rate. For example, true positive rate is simply ratio of correctly identified cubic structures to all of the cubic structures. And here the dashed diagonal line is basically equivalent to a random gaze. So ideally here in the ROC curve, we want to be as close to the left top portion of the curve as possible. So the area under the curve is a very important metric. And here, for example, it's 0.88. So I want to point out some of the nuances of actually performing classifier in practice. So for example, a lot of machine learning algorithms, including support vector classification, are sensitive to the pre-processing of data, for example, to normalization. So here, I deliberately kept the same data unbalanced without performing any pre-processing on the data, and evaluated the model again. And as you can see here, the area on the ROC curve dropped to 0.78, and also our classifier accuracy dropped to 0.78. And this shows that it's very important to normalize the data for at least SVC models. And this is not surprising, because if you think about it, in our variable set, we have, for example, variables such as atomic number, which is smaller than 100. On the other hand, we have melting temperature, which is in the order of, it could be in the order of the 1,000. So if we use those values, the model puts base and bias toward melting temperature, which may not be actually the case. So it's important to perform normalization in this case. Another important thing that I want to mention is that one should take care while dealing with unbalanced data. For example, I intentionally made the data set unbalanced by keeping only 5 hexagonal structures, which is only 1% of the cubic structures here in this case. And if you remember, our accuracy used to be 0.87, and with the unbalanced data, the accuracy turned out to be 0.73, which dropped, of course. But this is not too bad. This doesn't look too bad, because of course we have like less training data at this point, and so it dropped a little bit. But looking at the ROC curves, one could see that for the unbalanced data, the ROC curve is almost entirely on the guess line. So this means that our classifier doesn't have any power of distinguishing between cubic structures and hexagonal structures. And the reason that we have a reasonably high accuracy is because our test set is also part of our training set, which was already unbalanced, which was already contained mostly cubic structures. So, because the model sees cubic structure most of the time, it tends to predict everything to be cubic set. And we have a reasonably false high accuracy, but in fact, the performance of the model is no better than any lucky guess. So that's another thing that should be, it's important to be able to accurately evaluate the performance of the model and just not look at accuracy. For both of these case studies, I use simple compositional variables, but the truth is that the choice of variables is not, or feature set is not unique at all. For example, researchers have used descriptors based on only atomic connection in the crystal. So they haven't used any compositional information at all. And they were able to successfully model and predict properties such as formation energies, band gap values, bulk modulus, and shear modulus. And this is very interesting to me, because completely different set of feature sets is able to yield models with similar performance. For example, another example is that researchers have used partial radial distribution function as descriptors, and then calculated and predicted the density of state and Fermi level. So in my research group in the University of Houston, under the supervision of Dr. Brgoch, we've just started using machine learning in the past year. And since then, it's been amazingly useful for us, not only to predict properties, but also to guide our synthesis. For example, our former postdoc Anton Olinik used machine learning to predict crystal structure and look at the polyformisms of ABC phases. While he was using looking at distinguishing between TI-NI-SI type crystal structure and ZR-NI-AL type structure, he noticed that the prediction probability of some of these compounds is very similar to each other. So he thought that maybe they could actually coexist. And he went into the lab and picked titanium iron phosphide and went into the lab and synthesized it. And it turned out that both of these structure types coexisted in the same sample, which was very interesting to us. Moreover, we also have used machine learning method support vector classification to classify metals from non-metals, and also with high accuracy. And then we've used support vector regression to predict the band gap of non-metals. And what we did different here is that mostly these models are based on density function theory band gap calculation on the level of PBE, which is known to underestimate the band gap values significantly. So here we are able to gather a database of experimental bandgap, more than 2,000 experimental bandgap values, and it turned out that our model even surpassed the accuracy of PBE. And we are also able to, so in my research group, we showed that to get efficient phosphor, we can screen them based on Debye temperature. So high Debye temperature could potentially yield to efficient phosphor. So we use machine learning to model Debye temperature and then use that as screening, and we are able to identify a highly efficient phosphor. And Yaja, my lab mate, will give you more details about this project in the flash talk session. And finally, in my research group, we are interested in discovering super hard material. So in collaboration with the University of Utah and Dr. Sparks, we are able to use machine learned bulk and shear modulus of materials, and they use that to screen for potentially hard materials. And then we identified 2 compounds, and they turned to be the hardest transition metal carbide and borocarbide reported. So that again emphasizes that not only machine learning is interesting to predict properties, but more importantly, it could be used as a tool for experimentalists as well. So with that, I thank my advisor and my research group, and I'm happy to take questions.
All right, we've got plenty of time for questions and discussion. So yeah.
So the example that you had in the tutorial,
Right.
you have like 700 data points
Right.
and about 80 dimensional data.
Correct.
Is that data set seems like something that's very prone to overfitting? Should you do some sort of like dimensional reduction before you try that? Because for such a small length of data, size of data set,
Right.
you have very high dimensions. If
Um,
you don't do dimensional reduction, you're prone to overfitting.
So this is something that could be evaluated, right? So usually what we do is to also we use like dimensionality reduction method to just try it. It's a bit of also trial and error, and also feature selection method. But for this case, first of all, my interest was to make a simple model for the workshop, and not to like make the best performing model. But even then, with this dimension evaluating of the test set, we got fairly robust statistics. But also, the test set could be potentially a little bit correlated to the training set. That's also a possibility when you are talking about overfitting. But that's the best we could do at this point, right?
Any other? So in terms of questions, let's try and make it a discussion. If there's something you didn't understand, the morning is intended to be very much tutorial in nature. So if this is totally new to you, other people in here may have some similar questions. So feel free to.
So you distinguish the SVC and SVR by saying that SVC doesn't use a continuous,
Right.
continuous. I just don't understand
So,
the
all right.
fundamental difference.
Okay. So here, for example, so we have our training set includes of X values and Y values. For example, for formation energies, our X is our feature set. For example, we made that 80 dimension variable set, right? Based on compositional data. That's our X, right? And our Y is the label, is what I get, for example, from materials project. It's the corresponding formation energies. That's our Y, right? And it's a continuous variable, right? It's, for example, 1.3, right? And it could be 1.4, right? But for classification, for example, I use it for crystal structure classification. And I assign, for example, cubic structure to 0 and hexagonal structure to 1. So it's discrete. So our target or Y value is discrete here.
So it's a lot better to use it with the crystal structure analysis because you do want discrete values.
Yes.
You don't want in between.
Yes, exactly.
Okay.
Yeah, so I think so if you go really quick, Ari, go to the slide that's of the ABC phases.
ABC.
Yeah, the machine learning. So an example of this is that so support vector classification is always a binary classifier, always 0 or 1. So for ABC compositions, there's actually 7 common crystal structures. Okay, so basically we say we classify all compounds as titanium nickel silicide type would be 1, and then the other 6 crystal structure types would all be 0, right? So it's all binary classifier, and so we have in this right? This is just one set of the binary classifier. We had to do this 6 times, 7 times. So each time we would go through and show that we could classify titanium nickel silicide and separate it from the other 6. Zirconium nickel aluminide separated from the other 6. And so this is the way that the classification in SVC will always work, is it's always a binary approach.
So as far as regression goes, if you're doing some linear regression in a typical setting, you would also make a step of estimating uncertainties of those predictions in regression curves. So when you're doing regression in this context, you get uncertainties, and if your density functional values that you're saying are less accurate, if they are within those uncertainty intervals.
Was that the question? I thought you needed more explanation. So can you repeat your question? Sorry.
Do you estimate uncertainty of your regressor predictions?
Right.
Do you put uncertainty intervals?
So for support vector regression, it's possible to get the uncertainties, but they're not very reliable actually.
But in that case, when you're saying that your accuracy of predictions is better than PDE, that's
for that case?
Problematic statement, because you cannot say if your PDE values are within those boundaries or not.
So sure, that's a very valid point. Yes, as a whole, yes. But on a certain data that we've compared these two, it turned out that we had a better statistic. But saying that, that's the difference from doing the computational and machine learning. So ideally, you want to also include your uncertainty in the machine learning predictions, right? But for the computation, you're solving basically approximating the Schrödinger equation, which gives you better uncertainty. So,
no, it doesn't. That's the point that I'm trying to raise. That actually predictions in both quantum chemistry and machine learning are currently made in terms of point estimations.
Right.
They do not include uncertain propagation. And it would be natural to think that machine learning includes that step. It doesn't. So in that sense, you're sort of lowering the bar to the bar that is currently existing in the density functional theory of quantum chemistry, instead of raising the bar and including uncertainty evaluation. But if we're talking about making predictions that are actionable, it's really difficult to make them without uncertainties.
Yes,
well, that's not the question.
Okay.
I just want to add to that, there are certain machine learning algorithms which can deal with that, like Gaussian processes.
Yeah, but the problem is that with SVR or SVC that we use, you can't really get that, at least in a reliable manner.
I think this is a really good point. Is that a lot of sort of, at least in our case, we come from a DFT background, so this tends to be where we fall into, right? Is analyzing things within the context of DFT. And so I think that's a really interesting point. Like how do we think about putting this into more of a context of what an experimentalist would want to see? And I think that's a broader community problem for sure.
Yes, it is.
But I think that's a great point. Does anyone here have any ideas of that they've come across where you've seen the ability to do this type of error analysis? Because I'm not really. It's not something that I've ever come across. Do you have ideas, Bryce?
Oh, yeah. So the methods that we have implemented on our platform do uncertainty estimation. There is also this is a plug for a workshop. It's not my workshop, but there's a workshop on uncertainty quantification and machine learning for science and engineering. I think it's at USC. It's in June. Citrine's going to be there. Other folks are going to be there. It is an emerging research area.
Cool. Great. Thanks, Bryce. Other points of clarification or questions? We've got plenty of time. Yeah, right here in this front first.
So you said the choice of descriptors is not unique for choice of properties. Does that hold true for non-crystal systems?
For non-crystal systems, do you mean like amorphous material?
Yeah, the amorphous material, polymer.
Yeah, so there are some criteria that a descriptor should have, right? It has to represent what you're looking for. It has to be unique in a set. It has to be unique in a set that, for example, for all the here crystalline materials that I have, or for non-crystalline materials that you have. Then you assign a set of a descriptor to your compounds. It has to be unique within that system, right? Because then the machine could not distinguish. When I say unique in this sense, is that you can get completely different descriptors from different perspectives, but the descriptors should be unique, either for non-crystalline materials or crystalline materials.
Let your imagination run wild. That's kind of one of the fun things. And we do this, right? We put all sorts. So this 20 variables that Aria selected, we, in most of our work, use 150 different variables. And we're constantly thinking of other things. But I will regularly see things come across literature feed, and I'll say, oh, let's see if we can implement these ideas. Put it in. If it improves your model, great. And if not, then it's not something that we're interested in pursuing. That's kind of the way we go at it. But yeah, I mean, we often just sort of build as many as we can and then reduce it back down, following sort of the original first question up here. So, yeah, question up there.
Yes, hi. Tehrani from University. I had a question if you had used, say, for instance, Anomaly Detection, you get out feature affordances to figure out which features contributed the most to the model.
Which one?
Feature selection. How do we do feature selection?
Okay. So there are different methods of doing feature selection. So one of them is just simply eliminating like the descriptors one-to-one and then see how the performance changes. We've also used some genetic algorithm methods because that's very time-consuming. Like looking at each descriptor one by one is very time-consuming. So we usually use a genetic algorithm method to do that. There are also different methods. For example, in this case, Anton used a cluster resolution feature selection method. For these examples of the workshop, no, because I wanted to make the models as simple as possible, so I just randomly picked 20 compositional variables. But typically in the research, yes, that's how I use the feature selection.
Was the question also asking about feature ranking, though?
Yes.
Oh, so can you speak about feature ranking?
Oh, okay. So for the feature ranking, so one of the ways that I've personally done feature ranking is within the framework of PLS, because it gives you the feature score and VIP of each of the features. But the problem is that, and then you can see which features like rank the best. But the problem is that here, for example, if you're talking about supervised vector regression, because it's a different method and it's also at high dimension, it's very difficult to interpret. For example, maybe methods such as decision tree or random forest would be much better for this purpose to see which features actually contributed. But neural network is very complex to get. Support vector is high dimension, so it's not very interpretable.
So PLS is partial least squares analysis. That's not clear. And VIP is variable importance parameter. Tutorial, Aria, tutorial.
Yes. Just to follow up on your question on interpretation, so if you're doing support vector classification of this kind of data, does decision boundary give you any physical meaning at all about your research, like from your experience? Like?
No, I don't think so. That's just based on my experience. Also, another point that it's actually in the Nature publication that showed at first for the failed experiment, they've made a decision tree of their support vector model to be able to interpret which parameters for the synthesis actually useful. So that's also a trick that you could use.
Quite sure how to do that, but we're interested. So kind of to go along this, that's one of the drawbacks of the support vector regression or classification, is that it's probably, I would say, the blackest of the black boxes, right? In terms of your parameters that go in, so when Aria talked about doing a PLS analysis, that's not within the framework of the support vector classification. It can be, but generally it's not. And so to get some of these, say, variable importance parameters back out, you kind of have to go outside of support vector machine. And that's, in terms of sort of thinking about how do you inform experimentalists, that's maybe what you have to do, because you can tell an experimentalist what materials to look at, but at some point, you kind of have to tell them why. They're not as accepting maybe as other people.
This is an area that, like in material science or chemistry, probably should be even focused more on it, because at the end of the day, we are scientists and we don't just want some black box to work for us. It's interesting, but at the end, what's important is to what we could gain from it and what knowledge we could gain, so that we could also add to our knowledge. So that's the interpretability, interpreting the models, something that should be even focused more on.
Yeah. In your second case study, you talked about your initial data set as being balanced versus unbalanced, and I'm curious if that's a common descriptor when working with data sets, because sometimes you don't have the information to even know if you wouldn't want to call it that.
So that's a good question. So what I call for is that you have to deal with that with care, not that it's impossible to deal with unbalanced data. That's what people do all the time. For example, even for these cases, we are usually interested in the cases that we don't have much data on it. So one way is, for example, because I'm talking about SVC, I make the example from that. You could use the weighted support vector classification that sort of resolves this problem that I didn't perform here. Or alternatively, one thing that, of course, the best practice is that, if possible, gather more data on your unbalance or use different methods. It's not that we can't deal with unbalance. It's a whole set of it's a whole field to deal with unbalanced data. It's just that, for example, because this is one of the first things that I encountered myself. I was like, oh, we got a really good accuracy. Then I looked further. It's like, oh, it's terrible. So that's something that beware of, that you have to deal with this unbalanced data someday. It's not that it's not possible to deal with.
And I think it's one of those tough things too. I mean, when we submitted, when we got revisions for the band gap prediction, one of the reviewers' questions was actually about the balancing of the data. And effectively, they wanted to make sure that we were balanced in terms of non-metals versus metals in our prediction. And we kind of sat back and said, well, how do we know how many metals and non-metals there are in the universe, right? Because that was kind of something that we have so many that we can put in, and we sort of do our best to make sure they're balanced. But when they wanted us to predict and weight our training set accordingly, we said, well, we don't know how many there's supposed to be to represent our ultimate sort of overall prediction model. So yeah, you just kind of have to use the non-basic chemical intuition and say, well, this is reasonable. So we call it 50-50, and they accepted it.
Yeah. So then you're going to introduce human bias at the get-go in that scenario.
Oh yeah. Yeah, in terms of, I would say there's always, especially when you're talking about supervised learning, there's always some human bias. So there is always a graduate student sitting there doing this. So there is inherently bias. But I would say the bias is no worse than DFT.
Sometimes, so sometimes sometimes you cannot, people use bias model. For example, I've seen a lot of neural network, because we don't have, there is no enough data. So with this amount of data, you can't even make a reasonable model. So you can basically guide the model based on the scientific knowledge that you have. So it's one hand, it's biased. On the other hand, it makes it much more simpler and much more efficient. So it's a balance between that.
Yeah.
I have a question about the background prediction.
Sure.
So you mentioned the background predicted by the machine learning is more accurate than PDE. But PDE is know that it underestimates the background of some standard matrix. So may I ask what is the energy range you predicted for the background?
Sorry, what was that last part?
Energy range.
Yeah, so we have predict.
You have the regression.
I don't have the method. I have it in the laptop, but
Maybe they are electron. I mean, the donate of the background.
so that's a good question. We actually plotted the density functional theory band gaps versus our predictions in a plot. So ideally, we wanted our data to overestimate all of the band gaps, all the PDE band gaps, which it mostly does. But there is no trend, our model doesn't necessarily underestimate or overestimate. So it could
Yeah. So for the topological insulator, the band gap size might be many electron volts, but for semiconductor, it's several electron volts. I mean, which energy range do you predict?
The several electrons.
Yeah, for specify the type of material.
Yeah. So I would say, I mean, so it's across the entire range of 0 to 10. So certainly not in the lead.
Yeah.
Yeah, I mean, it would be standard semiconductors, think PV materials, insulators.
This model call is not good for that. Yeah, semiconductors and insulators.
And metals. I mean, so
And
the
metals.
one thing
Yeah,
that
for classification, we distinguish between metal and non-metal, and for regression, semiconductors and insulators.
Good question. Other questions? Couple more minutes. Let's thank Aria one more time. We'll take a couple minutes here while Kai switches and sets his talk up. So we'll take just 2-3 minutes. Grab more coffee, plenty of coffee. Grab more donuts.